All right, welcome back, everybody. Today we're going to be doing section 12.4, which is all about the cross product. So the last section was the one about the dot product, and we started by asking how could we meaningfully multiply two vectors and get, a meaningful result from that. Now we're going to answer that question again and get a new way of multiplying two vectors. Let me pull up the slides and we'll get started. All right, so here's the overview. So we're going to start with a motivating question, which is kind of like the one I just mentioned a moment ago. Then we'll get the definition of the cross product. Then we're going to talk about determinant notation. And for those of you that are taking linear algebra or are going to take linear algebra, you will see this notation used even more in that class. Then we're going to talk about geometric properties of the cross product, algebraic properties of the cross product, scalar triple products. Then we'll do a quick physics application involving torque. And then we'll see a couple of helpful Mathematica commands, kind of like in the last section. All right, so here's the motivating question. Yeah, when we were talking about the dot product, we found a meaningful way to multiply two vectors by multiplying the components and then adding the result. And that gave us information about the angle between the two vectors and how aligned the vectors are, how much of an effect one vector had on the other, that kind of thing. So in this section, we're going to develop a new operator called the cross product, and it's going to give us the answer to this question right here. This is the motivating question. If you've got two vectors in V3, so three-dimensional vectors, how could you find a third vector that is orthogonal to both of those vectors? That's the question, all right? So this is one of those times where I want you to just ponder this for a moment, and then we'll talk about how to do it. How could you find a vector orthogonal to two other vectors? All right, let's walk through it here. So let's just say our vectors are A and B, A1, A2, A3, B1, B2, B3, these two vectors right here. And then let's let C be the vector of interest that's orthogonal to those other two vectors. So we want to find a way to make sure that C is orthogonal to both A and B. Well, one thing we know from the dot product in the last section is that if these vectors are, sorry, if C is orthogonal to both of these vectors A and B, then that means the dot product of A with C has to be 0, and the dot product of B with C has to be 0. So we need both of those dot products to be 0. If we write that out in terms of components, we get this system of equations right here. Now, this is a system of two equations in three variables. So there's three variables here, but only two equations. So if we want to find a representation of C, all we really need to do is a bit of algebra. It might be a little bit messy, but it's just a little bit of linear algebra, frankly. We just need to solve this system for our three components, C1, C2, and C3, in terms of the other components, the components of A and B. And that's okay, right? Because what we really want to know is we want to be able to put two vectors into this operator and get out a vector that's orthogonal to both of them. So it's okay if these results are in terms of A and B. That's actually what we want, right? So let's start by eliminating C3. So what we're going to do is we're just going to use the elimination technique for solving a system. We're going to multiply the first equation by B3 and the second equation by negative A3. And then when you add the two results, the C3 terms cancel out. And then what you're left with is this. So when you add these two equations together, you end up with this equation down here. All right, so now we've kind of separated out things in a meaningful way. So we've got things separated in terms of the C's, C1 and C2, and now we can view these as the coefficients of C1 and C2. And we know the whole thing is equal to 0. Right, now this particular equation has this form. So if you look at the equation, this is just a repeat from the previous slide. But we can call this part P and this part Q. And so really the structure of the equation that we're looking at is this: P times C1 plus Q times C2 equals 0. And one of the solutions right off the bat that you can probably see from the solution you can see just by looking at it is that C1 could be Q, and then C2 could be negative P, right? So if this was Q, and this was negative P, then we would have 0. Could also like switch the order of the negatives and you'd have the same kind of result, but it would be off by like a negative. But that's really all we needed. That's all we needed. Because if C1 is equal to Q, Q is only in terms of A and B. And C2 would also only be in terms of A and B. So right now we have two of the components that we were looking for originally, right? C1 and C2. All right, next, if we want to get the last component, the last thing we need to solve for is C3. So we're going to take those two results, substitute them into that equation from above, and then now we can solve it for C3 just using some basic algebra. Go through the process right here, and then you find that C3 is equal to this. There we go. So what did we just find? We just found a vector that is perpendicular to the vectors A and B, and this is the form of that vector. So if A is A1, A2, A3, and B is B1, B2, B3, then a vector orthogonal to both of those vectors is the vector that has these as the components. That's it right there. And that, my friends, is what we call the cross product. So the cross product, or otherwise called the vector product of two vectors, is this vector right here given by those components that we just produced algebraically. So that's the definition of the cross product. One thing to keep in mind is this. So there's a few things here. First, the cross product of two vectors is orthogonal to both of those vectors. That was the beginning of the section, right? The cross product produces a vector that is orthogonal to two other vectors. So if you ever have a situation where that's what you're looking for is the cross product. The other thing to take careful note of is that the result of the cross product is a vector. So this is an operator where you put in two vectors and you get out a vector. Compare that or contrast that to the dot product, where the dot product is a scalar. So remember, the dot product, you put in two vectors and you get out a number related to those two vectors. So they're very, very different operations. They're very, very different processes. They give you different results and they have different purposes. So you really want to keep in mind which one you're working with. They're not the same and you can't really conflate them. They're not equal in any way. Another important point is that the cross product as we see it here is only defined when the vectors are in V3. So this is one of those situations where the generalization isn't as intuitive as you might think. There is a way to generalize the idea of a cross product with what is called a wedge product. Wedge products are things that you study when you start studying differential geometry and Riemann surfaces and things like that. Many of you will not be exposed to these things, but if you're wondering, as you should, like how could we generalize this to higher dimensions other than 3, there is kind of a way to do it, and it's called the wedge product. If you want to read about it, you can click on that link, and that'll take you to the Wikipedia page about exterior algebras, and it will take you down a very, very deep rabbit hole if you're interested. But it is a rabbit hole that is currently researched a lot. So if you want to go there, check it out. Um, Okay, so one thing I want to address is this. You might notice that this formula is pretty complicated, and I am not a fan of memorization. I generally say you shouldn't really have to memorize anything. There's usually very little that you should memorize, stuff that you want to be able to just pop out. Right. So I don't know how many of you were thinking this, but when I originally saw this a while ago, looking at this just seemed like a nightmare. Like, how am I going to remember that? I know I'm going to mess up all the products. I'm going to mess up which one comes first, which one's where. So to help us with that, we use what's called determinant notation. Um, the determinant notation is really just a structure that makes it easier to remember what this vector is. If you would like to memorize the vector as it's written, be my guest. Go for it. If you can memorize it and not forget it and not mess it up, congratulations. I would definitely mess it up. So I always definitely prefer the determinant notation. We're going to use determinants again later in this course. And like I mentioned earlier, you'll use it in computational linear algebra a lot. We will see it when we start talking about integration in higher dimensions, multiple integrals. Okay, so here is what they are. So you can have determinants of different orders. The first is a determinant of order 2, and it's defined like this. So this is the symbol that we use for the determinant, and this is the result. So when you see this symbol, really what we're talking about is this expression right here. And the way that you can think of it a little more intuitively is that you're basically doing this cross multiplication and subtracting the results. So it's A times D minus B times C. There you go, AD minus BC. So it's like doing this in a certain sense, AD minus BC. It might seem arbitrary, but it really is not. We can't go into too much of the details, but it's not an arbitrary choice for that multiplication to occur that way. Then, if you have a higher order determinant, this is actually one of those situations where it generalizes to any integer order that you would prefer. So if you want to talk about determinants of order 100, you can do it, but it'll be one of those moments where you you become thankful for computers because you don't want to have to deal with large order determinants by hand. Why is that? Well, because it's kind of a recursive relationship. Determinants of higher order are really defined in terms of determinants of lower order. So, what is a determinant of order 3? Well, you're going to rewrite it in terms of determinants of order 2. Then you would compute the determinants of order 2, and then you'll get a final result. You'll get a final result. Let me see, do I have it here? Yeah, let me start on this page, and then I'll show you again in the next page. The way that we're producing this result over here on the right-hand side is we're fixing one of these right here, and then multiplying that by the second order determinant that is produced when you ignore the row and the column associated with that. So you see here we have A1, A1, and then you get a lower order determinant. Let me, right here. Oops, can do that a little nicer, a little bit nicer. So that's how you get the first term on the right-hand side here. That's what that is. All right, then to get the next term, you kind of repeat the process just moving across the top row. So let me use a different color here. Let's pick pink. Now I'm going to fix A2, and then I'm just going to cancel out the, oh wait, no, I wanted black for that one, didn't I? Here we go. I shouldn't say cancel out. I should say ignore. We're going to ignore the row and the column associated with A2. And then what we're going to do is we're going to produce a determinant with the remaining entries right there. So you'll get A2 times a second order determinant B1, B3, C1, C3. And there it is. Oops. Like so. All right, that's the next term that you get. Moving right across the row at the top. Next, what we're going to do, let me pick a different color here. Maybe I'll use blue. Oops, forgot about this piece right here. Next, what we're going to do is we're going to fix A3, ignore the other terms in that row and column, and then focus on this second order determinant right here that's left over. So what you get is A3 times this determinant, just like so. And that's how it goes. So that's how the determinant notation works. One thing I want to point out that I know I say on the next slide too is you should take note of the difference or the change in sign. So notice this one is positive, but then this one is negative, and then this one is positive, and they alternate. So it's an alternating set of terms. That's really what it is. And that's how you compute the determinant of order 3. All right. So why is this so nice? Well, this gives us a really easy way of expressing the cross product using determinants, and then you don't really have to remember much. You just remember the standard basis vectors. Let me just, here we go. Just remember the standard basis vectors, put those in the top, and then do A1, A2, A3, B1, B2, B3, and then use that process that I just described a moment ago. There you go. Yeah. I changed the order of the multipliers here just to be a little more indicative of the vectors. So this would be like what I called A1, A2, A3, right? And then you have all these lower order determinants. There's that one. There's that one. And then there's this one. Oh, wait, is that a typo? I think I might have a typo. Oh, no, I'm sorry. This one. There we go. That's what it is. So again, note the alternation of the terms. That's a positive, that's a negative, that's a positive. And another thing that I want to mention is this right here. Technically, this is what we call an abuse of notation because the output of a determinant is actually a scalar. It's a real number, or a complex number, or whatever field of scalars you want to work over. But the reason that we're using this is that the shorthand is just very easy to remember, and this is all you need to do to compute a determinant. So this really is an abuse of notation. And if you follow this link to the Wikipedia page on determinants, you'll get more information about what a determinant actually is. All right. Okay, so let's practice. And this is one that I want you to try on your own. So I want you to try to find a vector orthogonal to A and B using that determinant notation that we just reviewed right now. So think about how you're going to use it, how you would set it up. And then just to get the juices flowing a little bit, say something out loud to whoever, the wall, yourself, your cat, your dog, your sparkly water, whatever, and say what you're going to do. All right, now try to compute it. So compute the vector that is orthogonal to these two, and we'll do it together in a moment. All right, so let's try this on our own. We're going to use that determinant notation. So here is the setup. Across the top, you've got the standard basis vectors. We've got our first vector A on this row and our second vector B on this row. And then we're going to do those second order determinants, right? So if I take I and I get rid of those, this is the determinant I get. Now if I take J and I ignore those, this is the determinant I get. Then if I take K and I ignore those, this is the determinant I get. And then now you use that cross multiplication for second order determinants that we saw on the previous slides. So this gives you this, and then this gives you this, and then this gives you this. Now what you have is just a bunch of arithmetic at this point. So simplify these expressions here, and then you'll get your vector. So this is a vector that is orthogonal to both of these two vectors right here. And that's what the cross product gives us. Pretty cool, huh? Okay, so we know that the vector A cross B is orthogonal to both of those vectors A and B, but one question is which direction? Because, if I've got two vectors, I could be this way or I could be that way. Those are both orthogonal to A and B, right? So which one does this produce? It can't be ambiguous if it's going to be a function, right? It's got to actually produce one result. Well, the good news is that it obeys the right-hand rule. So if you want to know which direction this orthogonal vector is pointing, you use the right-hand rule, where I can't show you, A curls to B, and then the direction of your thumb is the direction of the cross product vector right here. There you go. So the right-hand rule comes in handy once again. Pretty nice. All right, now a kind of cute result is this theorem right here. So if theta is the angle between two vectors A and B, remember the angle has to be between 0 and pi inclusive, then it turns out that the size of this vector, the size of the cross product vector, is size of A times size of B times sine of theta. So it's kind of cute. It has this like formulaic similarity to the result of the dot product, right? It's not the same thing. It just happens to be that they have a similar structure in this case. So this one I think is definitely one worth proving, just so that you can see it's not some totally arbitrary thing that was made up. So here we go. Right. So by definitions of the cross product and just vector magnitude, the size of a vector, we get the following very lengthy calculation. um, the calculation is definitely not above you. It is purely just algebra and arithmetic. It's just long and messy. That's about it. So what do you do in this situation here? You FOIL it out. You distribute the whole thing out, and you do that for each one of these three terms. And when you do that, you get a very long line of terms, which is right here. I want to point out this continues, so this line continues to this other line here. Then what you can do is you can factor part of it, and you can factor another part of it, so you get this. There you go, really just kind of performing factorization. And then the thing to recognize is that this expression right here is the magnitude of A squared. And this one is the magnitude of B squared. And then this one right here, that's the dot product. That's the dot product of A and B squared. So we get the next line right here. Right. Now, remember that one corollary we had from the previous section about the dot product, right? So the dot product you can write in terms of the magnitude of A and B and cosine of the angle between them. So just a little refresher. If you remember, A dot B was equal to length of A, length of B, cosine theta. So we can use that to get this right here. Oh yeah, whole thing gets squared. And then you end up with this second line right here. The next line, I should say. All right, well, good old algebra once again, or good old arithmetic. We can factor out an a squared b squared, or length of a squared b squared from both of these terms. And then over here, we're left with 1 minus cosine squared, which is just the good old Pythagorean identity. That's equal to sine squared of theta. Right. Now what we can do is we're going to take the square root of both sides. And because we know that sine of theta is always non-negative, it's always greater than or equal to 0 when the angle is in this interval, it must be the case that we're taking the positive result of the square root. So we get sine of theta, and there's the result. That's it. All right. So if you ever need to know the length of that vector that's orthogonal to A and B, you can just use this formula right here. Length of A times length of B times sine of the angle between them, and that'll tell you the length. All right. Now, as a corollary to this, we get a couple corollaries. For one, we have a way of determining if two vectors are parallel, and we can do it just through a simple calculation. So two non-zero vectors are parallel if and only if their cross product is 0. So what that means is if you try to cross two vectors and you get the 0 vector, they must be parallel to each other. The proof is also very quick. It's a little bit reminiscent of the proof that two vectors are orthogonal if and only if their dot product is 0. The only way two vectors could be parallel is if the angle between them was 0 or pi. That's the only way they could be parallel. In either case, sine of theta is going to be 0 because sine of 0 is 0 and sine of pi is 0. So that means that the length of the cross product is going to give you 0. There you go. Now, the only way the length of the cross product could be 0 is if the cross product itself was 0. That's one of the unique properties of 0. It's the 0 vector is the only vector that has 0 length, right? Unless, yeah, that's it. So that means it must be the case that that cross product is the 0 vector. There we go. So yeah, there we go. So two vectors are parallel if and only if the cross product is 0. Right, now, another helpful corollary we get is this one. The magnitude of that cross product, length of A, length of B, sine theta, turns out that's actually equal to the area of the parallelogram formed by the two vectors A and B. So this is one of those times where I just want you to pause for a minute and just let this marinate in your brain for a second here. The magnitude of this vector happens to be equal to the area of the parallelogram formed by those vectors. So stare at this for a minute, think about it for a minute, and then, well, I'll say the proof out loud. The proof is one line at the bottom. Okay. All right, so what is the proof? Well, the area of this parallelogram formed by the vectors A and B is just given by the classic area formula for a parallelogram, base times height, right? That's the area. Area of a rectangle, basically, except this piece, came from over here. So base times height. Well, what is the base of this parallelogram? It's the length of A. And what is the height? Well, the height of the parallelogram is the length of this line right here, that line segment. And using basic right triangle trigonometry, we can see that the length of this is length of B times sine theta. So the area of the parallelogram is length of A times length of B times sine theta. But hey, that is the size of the cross product. That's the length of the cross product. So there you go. Pretty wild, huh? Turns out that we're going to need this interpretation later when we get into chapters 15 and 16 and we start doing surface integrals because well, you'll see, I don't want to get too far ahead. This is also a very helpful interpretation if and when you learn about differential forms, which are basically a generalization of a structure that we're going to use when doing multiple integrals. This is also where wedge products come into play if you want to start talking about higher dimensional versions of these things. For us, we're going to keep things simple and just stick to this parallelogram, and we will see it again when we get to these chapters, chapter 15 and 16. Right. Okay, so now here's one I want you to try on your own. It's not too hard. You already have the skills to do it at this point. I want you to try to find a vector that's orthogonal to the plane that passes through these 3 points. So remember, any plane is uniquely determined by 3 non-collinear points. So I want you to find a vector orthogonal to that plane. So start by thinking about how you might approach it. Right? Now say something out loud to anyone, your classmate, your peer, to yourself, about how you would go about it. How could you possibly do this? Okay, now try to work it out on your own. See if you can find a vector orthogonal to this plane. Right, here we go. So let's do this one together. I think the first thing is if we're trying to find a vector orthogonal to a plane, we're probably going to use the cross product. It'd be nice if we could use the cross product. It gives us a vector that's orthogonal to 2 other vectors. There is a preliminary step that we need, though. We actually need 2 vectors to put into the cross product. So using these 3 points, we need to produce 2 vectors, which luckily we can. We can just take vectors connecting these points pairwise and then use the cross product there. You can kind of choose whichever ones you want. We just need any vector orthogonal to the plane. So in this case, I picked the points PQ and PR, and I just found the displacement vectors between them. So here's the displacement vector between P and Q, the displacement vector between P and R, and then those are our 2 vectors. Throw that into our determinant notation and compute the cross product. So again, remember we like fix I and do this determinant, and then we fix J and do this determinant, and then we fix K and do this determinant. And that'll give us these coefficients for I, J, and K. Basic arithmetic after that, and you get, boom, this vector right here. Cool. So that is a vector orthogonal to the plane that contains those 3 points. Now let's talk about some algebraic properties. We saw the geometry of the cross product. Now let's look a little bit more at the algebra. One thing that can help is if you look at the cross products of the basis vectors I, J, and K. So you get these cute results from doing the cross products of these. I will leave the algebraic part of this, the calculation, to you if you would like to verify it. But also, you can just use the right-hand rule. In fact, I think I say that. Do I say that? I think I say that somewhere else in here. um, you could basically figure out what this is going to be by using the right-hand rule. If I cross I and j, then the vector that's orthogonal to I and j is the vector k, using the right-hand rule, right? There you go, the vector k. If I cross j and k, I get I. If I cross k and I get j. If I switch the order here and do j cross I get negative k, because now I'm going like that. Same thing with kj, I get negative I, and then I cross k is negative j. Oh yeah, I say it right here, right-hand rule. There it is. All right, so one interesting property that we can see from this right away is that the cross product is not commutative. Not commutative. So this is an important thing to keep in mind. If you wanted to switch the order of these, you're not going to get the same result. So it's not as nice in that sense as, say, the dot product, which is commutative. Remember, with the dot product, it doesn't matter which order you dot, you get the same number as a result. In this case, the result is different. In fact, the result is opposite. So here, I cross j is equal to k, but j cross I is equal to the opposite of k. So equality does not hold there. It's like an anti-symmetry that you've got instead. Another cool thing is this. So if any of you are interested in, say, like video game design, I know I talked to one student about this, and he actually mentioned a really cool three blue, one brown video about this. But if you want to read up about the quaternion number system, it's a very, very helpful number system if you want to do like video game design because it helps you compute three-dimensional rotations very quickly using this new number system. The quaternions are like an extension of the complex numbers. You might remember the complex numbers are an extension of the real numbers. Well, you can also extend the complex numbers and you get what's called, well, you can extend them in a particular way. And then what you get is what's called the quaternion number system. So check it out if you're interested. It's pretty cool. Uh, another thing. So check this out as well. If I cross I and J first, and then I cross it with I get negative J. Right? But if I cross I with itself first, and then I cross it with J, I get the zero vector. So in other words, we also have the fact that the cross product is not associative either. So this is one of the reasons that it's really important to think about these operations as operators. And operators may or may not have certain properties that you become so accustomed to working only with real numbers. Real numbers are just so nice, right? So real numbers with multiplication and addition, multiplication and multiplication and addition are commutative with real numbers. They're associative. Everything is super nice. In this case, this operator is not as nice. So if you start changing the order of things in your cross product, you're going to get different results. So be very, very careful there. Now, because of these subtleties, it's good to kind of write out what the properties here actually are. So here are some of the properties of a cross product. This one we saw just a moment ago. A cross B is equal to the opposite of B cross A. So if you want to switch the order of A and B in a cross product, you got to take the negative too. One nice thing is that you can move scalar multiplication through the factors of the cross product. So that is one nice thing. If you do K times A and then cross B, you get the same result as if you just multiplied A cross B by K. And you could even scale B first and then cross it with A on the left, and then you would get the same result. So scalar multiplication does move through the cross product, which is nice. There's a distributive property. So A cross a sum of vectors is equal to doing A cross B plus A cross C. So there's a distributive property, which is nice. The distributive property also holds from both sides. This is one of those subtleties. So math majors pay close attention to this kind of thing because when you get into abstract algebra, you have to be careful about which side you're doing things on because commutativity is not always guaranteed. Commutativity is just a really, really nice property, but you don't always have it. So I need to actually say explicitly the difference between this and this because here I'm multiplying on the left. Here I'm multiplying on the right. And because the cross product is not commutative, these two things need to be proved separately. Thankfully, it actually does work. So the distributive property works this way, and it also works that way. So that's one of the nice things. Another nice thing is this one right here, this relationship between the dot product and the cross product. So A dot B cross C is the same as A cross B dot C. And then this one is kind of a funky one, but if you wanted to do A cross B cross C, you can actually rewrite it like so. Right. Yeah, so this one yeah, take a look at these, ponder these. I just noticed a note on my next slide. Look at these properties for just a minute and let them kind of sit in your brain for a minute. All right. This one in particular is a good one to kind of like think about because I've got a cautionary note for you. There's a lot of different mathematical objects and a lot of different operators flying around with each other at this point. So you really, really have to try to keep track of what the results of these operations are. Because remember, yeah, like I say it right here. Remember, the dot product gives you a number, The cross product gives you a vector. And it's non-trivial to think about how to multiply vectors or scalars and vectors or scalars and scalars and there's all these combinations going on, right? So you really, really have to take time to think about what are the results of these operations. Yeah, we're working with scalars, vectors, scalar products, vector products, all sorts of things. So this is a good one to take note of because what is this? What do I mean right here? Actually, let me say this. What do I mean right here? What's going on here? What operation is occurring here? Think about it. Right, now say something out loud. What operation do you think is occurring there? Okay, well, let's think about what is coming out of some of these operators. A dot C is a scalar. So what I do is I'm getting a scalar, a number, and I'm multiplying it by B. So I'm scaling B. So the operation that's going on here is just scalar multiplication of a vector. Same thing over here. This is just scalar multiplication of a vector because A dot B is going to be some scalar, some real number. So that's what's happening there. Scaling B by this, scaling C by this, and taking the difference. And you get a vector. Okay. That one. All right, now building up from this, you can also talk about scalar triple products. So scalar triple product is this. Oops. A dot B cross C. Again, it can be expressed using determinant notation, using just the original component equations that we derived for A cross B. Here, instead of having ijk at the top, we've just got the first vector A right here. So A1, A2, A3, B1, B2, B3, C1, C2, C3. But the process of computing the determinant is identical. Nothing has changed there. So it's like you fix A1 and then do this determinant. You get that, right? So it's like A1 times this determinant. Same thing here, fix A2, and then you get A2 times this determinant. There you go. And then fix A3, multiply by this determinant, and you get that. And what's kind of cute about this is maybe now you can actually see that this really is A dotted with B cross C. It really is A dotted with B cross C because if you think about it like this, A1, A2, A3, that's like the vector A1, A2, A3. And then these pieces right here, these pieces are the vector that you get when you compute the cross product. So it is quite literally A dot B cross C. Oh, it should use different colors. Literally is A dot B cross C. There you go. Cool stuff. Now, what is so interesting about this scalar triple product? Well, this is kind of a mouthful, but the volume of the parallelepiped determined by three vectors, the three vectors A, B, and C, is actually the magnitude of that scalar triple product. Scalar triple product. Oh, one thing I forgot to mention is this. I'm going to point this out. There's a reason that it's called the scalar triple product. It's because the result of this product is a scalar, it's a number, right? Which makes sense because the result of the dot product is a scalar. So that's why I'm emphasizing the word scalar here. When you compute the scalar triple product, what you get out is a number. You get a scalar related to those three vectors that you're combining in this way. And what's nice is that when you combine these three vectors in this way, and then you take the size of the number that you get, that number is, that positive number is the volume of this parallelepiped that's formed by the three vectors. A parallelepiped is basically just kind of a skewed rectangle. I think you can probably see it from this picture here, right? But what's happening here is you're taking a rectangle and you're basically skewing it along some vector. And if you want to find the volume of that, you can just compute the scalar triple product and take the absolute value, and that'll give you the size of it. Now, as a corollary of this, this lets you determine if any vectors are coplanar. So coplanar vectors mean they all lie in the same plane. And what this corollary gives us is that three vectors are coplanar if and only if their scalar triple product is 0. All right, now ponder this for just a minute here. Let me throw up the thinker. Think about what this corollary says and see if you can make sense of it by using this picture right here, this figure. All right, so maybe it makes a little more sense now. If my three vectors are coplanar, then that means they lie in the same plane. So imagine this vector A being down here. Well, if A, B, and C are all in the same plane, then the parallelepiped that they would produce has no height, at all. Its volume is 0, right? That's the idea. Right, now you practice this one. So use the scalar triple product to show that these three vectors are coplanar. So think for a minute about how you're going to do it. Right? Say something out loud about how you're going to try it, maybe even just the formula you're going to use. And then work it out. So try to compute it and see if you can verify that these vectors are actually coplanar. All right. The calculation is straightforward. Just use that determinant notation, throw these three vectors into it, and then hopefully you get 0. Let's check. There we go. So here's our determinant. Just like before, fix 1, do that determinant. Fix 4, do that determinant. Fix -7, do that determinant. Do all these determinants, add up all the results, and you get 0. Boom. Verified. So these vectors must be coplanar. They must lie all in the same plane. Now, moving along, we can apply this. This is a simple physics application, torque. As you might imagine, finding vectors that are orthogonal to other vectors is a common need. We have to do it a lot, and we need that a lot. So it gets used in physics a lot. For example, when you're investigating torque. So if you've got a force, F, acting on some rigid body at a point given by a position vector r, then the torque is the cross product of those two vectors, the position vector and the force vector. This is a really good illustration of how you can imagine torque. So basically you've got, this is the rigid body. This is like the wrench, right? And what you have is you have a position vector. Here's the center of the bolt that you're going to turn with the wrench. This is the length of the wrench, or I should say it's the vector that's pointing in the direction of the handle, and its length is the length of the wrench from the center to the end. And then you're going to apply a force at the end. So this is quite literally cranking down a wrench, right? So you've got a position vector, you've got a force vector, and if you take their cross product, what you get is you get a vector that's orthogonal to both of those, and it's going to shoot out like this. Well, shoot out like this, but these are parallel. There you go. If you want to know the magnitude of the torque, you just take the magnitude of the cross product. And we know the magnitude of the cross product using that formula that we proved earlier in the lecture. Right. So let's try this one. A bolt is tightened by applying 40 newtons of force to a 1/4 meter wrench as shown. Find the amount of torque being applied about the center of the bolt. So this exact situation. You've got oops, yeah, that's right. You've got a position vector, you've got a force vector, and just want to find the magnitude of the torque, so the size of the torque. This one's pretty quick, so I'll just kind of go through it on my own. Use that formula. The length of R is 0.25 meters. The size of the force is 40 newtons. The angle between the two vectors is 75 degrees. And then, oh, remember the angle has to be between 0 and 180, right? It has to be between 0 and pi. So that's why we picked this angle instead of this angle right here, because this one would be, oh, wait, hold on a second. 0 and 180, wait, what? Hold on, just lost my train of thought here. Angle between, Oh, yeah, because it's going in, right? Yeah, direct. Yeah, we want it to go in. So we're gonna pick, yeah, this one. So it's gonna go into it. So here we're basically taking this direction. Oh, we did R cross F. So R cross F is going, oh my gosh. There we go. Yeah, exactly. So I was trying to think of the right hand rule because the bolt is going to go, yeah, if the bolt is right threaded, then it's going to go in, so into the screen. Now we only needed the size of the vector, so you can use a calculator to get this, to get an approximation of sine of 75 and multiply it by 10 right there. Um, and we only needed to know the size, and that's what we got right here. The actual size is this. If we wanted to know the vector itself, then we just take the size of that torque and multiply it by a unit vector that's in the direction of the torque vector. Right. Now, there's a lot of formulas in here, a lot of different formulas involving the cross product. So this is a good time to think about how can Mathematica help us? How can technology help us? Well, the good news is Mathematica naturally can compute cross products. You just use the command cross, or you can call that command by typing escape, cross, and then escape again. Mathematica can also compute the determinant of any square matrix using the command det. And if you want to compute a scalar triple product, you can just use the det command again because of the way the scalar triple product is defined. So we're going to do that right now. Let me switch over to Mathematica. And maybe what we'll do is we'll pick out some examples from the slides here and verify them using Mathematica. Here we go. All right. So actually, wait, let me go back. Give me a sec. Let me go back to maybe find a simple cross product here. Okay, here we go. Let's try this one. Let me flash back to the slides for a sec. Um, we had to, yeah, so remember we computed the cross product of these two vectors, and this is the result we got. Maybe we can do the same thing in Mathematica and see what we get. So let me switch back to Mathematica, and I'll start by using the cross command, and then I'll show you how to do it by doing escape, cross, escape. So cross, and then to enter the vectors, you just write them in curly braces as a list. So the first vector was -2, -3, 1, comma, next vector 2, comma, 4, comma, 2. And then I hit shift return, and that's the vector it produces. Boom. What was the vector that we found? Let me flash back. -10, 6, -2, which is exactly what we just computed right there. Cool, huh? Let's use the escape. So what you could also do is this. If you don't want to type cross and then those, you can actually just do like vector cross vector. So what I'm going to do now is write the first vector as -2, -3, 1. And then I'm going to hit escape. And then it brings up this little like 3 pink dots kind of cursor here that lets you enter like a shortcut command. So I'll do cross. There you go. And then I'm going to hit escape. And now it actually gives me the little times symbol. Then I'm going to do 2, 4, 2, shift return, and it gives me the cross product right there. Yay! Pretty cool, huh? Let's look at that det, right? The determinant function for Mathematica. So let me do this. We're going to stick with this example for a minute. Let me go back to the slides. Remember that we used this determinant notation here for a shorthand to compute the cross product, right? Well, let's do the same thing. Let's use the determinant operator, the determinant command in Mathematica, plug this in and see what it gives us. All right, so I'm going to go det. And one thing to keep in mind about this function is that it actually computes the determinant of a square matrix. So it requires you to enter things as like a single object. So I'm going to put some curly braces right there. And then I'm just going to list my 3 entries of my 3 by 3 matrix. So if you remember, the top line was ijk. So ijk. The next line was our first vector, which was -2, -3, 1. There we go. And then the last line was our second vector, 2, 4, 2. There we go. And now I'm just going to hit Shift Return, and voila, there it is. So the same vector that we just computed, now written in terms of those standard basis vectors. One of the nice things about Mathematica is it does symbolic calculations. It doesn't have to be numbers. You can just use symbols. So here it's literally doing the determinant where these entries are any symbol you want. You could even do, there you go. But obviously for our purposes in this question, this is much easier to make sense of, right? So here's 3 different ways that you can use Mathematica to compute that cross product. Next, let's use it for scalar triple products. So let me go back to the slides. Let's take a look at that scalar triple product that we computed. This one, yeah, this one right here. So this is one we did right here. This is the scalar triple product. Oops, scalar triple product, where are you? There you are. And again, we computed it using the determinant notation. So let's do that here. Let's do the determinant that's pictured here in Mathematica, and let's see if it gives us 0. That way we can verify that we did all this arithmetic correctly. So here we are again, DET, and then we need to enter it as a matrix. So first initial set of curly braces, and then I'm just going to list those 3 vectors. So the first one was 1, 4, -7. The second one was, oh, notice Mathematica actually gives you, it auto-fills the second brace. 2, -1, -4. And then the last one was 0, -9, 18. Shift return. Oop, wait, did I enter something wrong? We should have gotten 0 from this. Ah, yes, there is an error here. This is one of the reasons we like technology, because it should agree with what we computed by hand, right? I realize I have a typo here. The first vector is 1, 4, -7, but the second vector is 2, -1, +4. And then the third vector is 0, -9, 18. Let's run that again. Boom, there it is. Nice. So, helpful Mathematica commands. Technology can be your friend as long as you know how to use it and don't overly rely on it. All right, let's see. I think that's about it. Yeah, we covered those last Mathematica commands. So on that note, let's play. I'm super excited to do this one with you all in activity. The next section is 12.5. That's when we finally learn about lines and planes. Thanks again for listening. I won't dwell too much. I'll see you all next time.